Hello everyone and welcome to day 5 of logarithms. Today we're going to be talking about compound interest and Newton's law of cooling. The idea of compound interest is a bank account will tell you that you get interest over the course of the year. And if you get a monthly bank statement, you're going to see that you get interest each month. That's due to the fact that your bank account may compound your interest rate monthly. And you're going to see how that works in your favor actually than compounding it once a year. So the idea of compounding is the idea that you actually make more money over the course of the year. So let's look at this. A person invests $500 into a bank account and has a nominal yearly interest rate of 4%. How much would this investment be worth in 10 years if the compounding frequency was once per year? So let's go the basic one. It only gives you interest one time a year. So this is a exponential function. Y equals our initial value, 500, times, we're increasing, we're not decreasing. We don't want the bank to take our money. If we have money set in there, we want to actually make money. So 1 plus our 4% can be written as 0.04, so 0.04, raised to the t. Well, in this case, we have 10 years, so we can make that 10. Cross off that t and make it 10. And we go to our calculator. I'm not going to do that right now, but we're going to have $740.12. So just by having $500 in your bank account, and if your bank said you were making 4% interest, you would leave in 10 years with $740. Hey, nice. I had $500 in there. Now 10 years later, I have $240 more. That's good. But what happens if we were to apply that interest 4 times per year, so quarterly instead of yearly? Here's the thing. If we're still making a nominal interest rate of 4%, so that's your overall interest rate, that's the interest rate the bank is going to say they give you. If I do this as 500 times 1 plus 0.04 raised to the 4, that's really over 4 years. We know that the bank is not going to give us 4% every quarter. That would be crazy. They would be losing money. So what they do is they say, okay, we're going to give you 4% over the full year, but we're going to give it to you quarterly. We're going to give you how much each quarter. Well, 4% is 0.04, and they're going to do each quarter. Quarters are 4 quarters in a year, so they're going to give us 1.01 or 1% each year. And so that's why it would not make sense. This would actually be doing it over, they would be giving you over 16% in 1 year. And that just doesn't make sense. They would really be doing it 1%. So actually I skipped over to C. So if you were told that an investment earned 4% per year, how much would you assume to be each percent? How much would you assume to earn each quarter? Really just 1%. And we talked about why. It's really 0.04 divided by 4. They're going to give you the overall nominal percent over the entire year. So how much are they going to give you each quarter is 1%. You do 1 plus 1 plus 1 plus 1. There's your 4%. But what we're going to see here is that it's actually going to make it better for us if they do it compounding quarterly, because you're actually making interest every quarter instead of just one time a year. So now let's look about how much this investment would be after 10 years. So we're going to do the same thing. We still have 500. But in this case, we're going to do this idea of this 0.04 divided by 4. Now, how many times was it compounded? It was compounded 4 times each year. And so 4 times each year. For the 10 years, we're compounded a total of 40 times. Because quarterly for 10 years, it's a total of 40 times. This is going to give us $744.43. Look at that. Just because we compounded it quarterly, we actually made $4.31 more. Now, a big difference? No, but it's extra money. And it's going to get even bigger if we do it over monthly. Not by a lot, but at least it's going to get a little bigger. What I want to do right now, and then I want to go back to number 2, is this idea of if we're compounding at a rate more than 1 year, what does it look like? So we always have our initial value P. That is our initial value. What do we start with? We always have 1 plus because we're making money. And it's this idea that we did right here. What is our interest rate? Our nominal interest rate, our R, divided by the number of years compounded. So 1 plus R over N. And then how did we figure out how many times to compound it? Well, it's how many years it is multiplied by how many times it's compounded, so T times N. And so with this, let's actually do number 2. How much would $1,000 invested in a nominal 2% yearly rate compounded monthly be worth in 20 years? So let's use this formula. So we have our initial amount, 1,000, 1 plus our yearly rate, remember this is 0.02, divided by monthly. Monthly is 12 times. We have 12 months in a year. Raised over 20 years. So 20 times 12. That's a multiplication symbol. And if we do that, you will get $1,491.33, choice 2. And let's look at that in the calculator just so we make sure that we get it correct. Parentheses, 1 plus. Use the alpha y equals, well, you should have 1 plus there. Why there isn't 1 plus? There we go. Use the fraction button. You do not want to let that be the mistake. 0.02 divided by 12. Notice that the 1 plus is on the outside of that fraction. And the parenthesis raised to the number of years 20 times the number of times compounded 12. And you'll see that we got the correct answer. Notice that the 8 rounds the 2 up to the 3 because we are in cents. So on to number 4. An investment with a nominal interest rate of 5%, so we're at 0.05, is compounded at different frequencies. Give the effective yearly rate. So the nominal rate is just how much the bank says they're going to give you. The effective yearly rate is how much the actual interest did you make. Accurate to 2 decimal places. So looking at a quarterly. Quarterly means 4. And so therefore we're going to have our effective yearly rate 1 plus 0.05 divided by 4. Now effective yearly rate means that T only equals 1. So even though we have the NT, our T is 1, so it's just going to be raised to the 4. Because that's how many times we compounded each year. And that is going to be equivalent to 1.05044, and it keeps going on, I know, if you do it in the calculator. And that's equivalent to 2 decimal places. And so the 1 just shows that we're increasing, so we move it over 2 decimal places, 5.04%. So we gain an extra 0.04 of a percent, better than nothing. Now if we go to monthly, we better be making a little bit more because we're compounding it even more. So 1 plus 0.05 over 12, all raised to the 12 this time. And that's going to equal 1.051166 and so on. Again, the 1 shows that we're increasing, so move it over 2 spots. We're going to get 5.12%. Okay, so we raised 0.08 of a percent. Again, we're getting better. Getting even higher percentage here. And daily, I know you guys can do this, so that's why I'm doing it out for you here. We raise it to the 365, we're going to get 1.05, and this time 1, 2, 6, da da da. So if we move it over 2, we're going to get 5.13%. So we raise it 1 more hundredth of a percent here. So you'll notice that we really had a bigger increase from quarterly to monthly than monthly to daily. So anytime you're given a compounded interest formula or interest problem, you're going to use this formula here. But what happens if we compound continuously? What happens if we keep gaining interest? And in reality, that doesn't happen in your bank account. So we'll just state that. It does not happen in your bank account, but it does happen in our next section of the notes. So let's just talk about what happens when we do gain interest continuously. Notice that we have our number E here. And it's the same idea, except for the fact that we have our initial value, E raised to the rate times t. This rate does not have a 1 in front of it. Please note that. It does not have a 1 with it. So do not expect, do not put that 1 in front. It's just the rate that we're talking about. So we have a $350 at a nominal interest rate of 2%, compounding continuously. So let's write an equation. A of t equals our initial value, 350, e to the r, 0.02 t. Done. That's it. So how much would the investment be worth after 20 years? Let's put 20 in there. So let's go to our calculator to see what that would be. So we're going to get 350 E second ln 0.02 times 20. And 522.1. And notice that the 8 rounds it up to the 4. So 522.14. So $522.14. Okay, not too bad after 20 years at only 2%. C, algebraically, so not using the calculator, determine the time it will take to reach $400, round to the nearest tenth of a year. So now we don't know what t is. We're solving for t. We have to say 400 equals 350 e to the 0.02 t. Here it is, coming back to the idea that exponential functions, when we have the variable in the exponent, we're going to have to use an idea of logarithms. So what do we have to get rid of first? We have to get rid of that 350. So let's divide by 350. So we're going to get 400 over 350 equals e to the 0.02 t. Now, let's look at this. Is the e alone, basically? Is there anything else being multiplied or added to it? And the answer is no. So with this, when we see e, we now have to think, what is the inverse of the e to some variable? And that's the ln. And so what we need to do now is take the ln, the natural log, I should not say the ln, take the natural log of both sides. When I take the natural log of both sides, remember the natural log and the e, base e to a number, or to a variable, the exponential function, are inverses of each other, and therefore we're left with ln of 400 over 350 equals 0.02 t. We're going to divide by 0.02, and let's go to our calculator. The ln of a fraction of 400 divided by 350 and the parentheses, all divided by 0.02. And you'll notice here we said to round to the nearest tenth, and so the tenth is 6.7 years. So we have t equals 6.7 years. Okay. So when you see an exponential function with base e, you're going to have to take the natural logarithm if you're trying to solve for an x variable in the exponent. What's the effective annual rate of this? So what we are going to do here is we're going to take e to the 0.02, and the t was just 1. That's how we did it above. When you do e to the 0.02, remember again, how do we get e? second ln, though, 0.02. We're going to move the decimal place over 2, so we're going to get 2.02. Okay, that should not have an equal sign. That's the effective annual rate. So that implies the effective annual rate. Okay, moving on to Newton's law of cooling. It's this idea that a liquid cools continuously at a continuous rate. It doesn't cool at every 5 minutes. It doesn't decide to cool a certain amount. It's cooling at a continuous rate, and that's what we're going to be talking about here. So let's look at the first exponential function they give us. F of x equals 8 to the 1/2, 8 times 1/2 to the x. If we use our calculator, I'm not going to do that right now. You can do it. So we have our initial value of 8, and we know that we're decreasing by about 50%. So if we think about it, if we have our table here, x, y, our 0, our initial value is 8, 1 is 4, 2 is 2, 3 is 1, 4 is 1/2, 5 is 1/4. So we're basically at 0. So if we think about it, it's going to look like this. And getting really close to 0. Now, clearly the y value gets smaller. We just stated that right here. Does it ever reach 0? Well, I can keep going. 1/4 to 1/8, 1/16, 1/32, 1/64, 1/28, and you get the idea that are we ever going to reach 0? And the answer is no. Every time we cut in half, we get closer to 0, but it will never reach 0. It's always going to be 0.0 something, right? So we're going to get very close to 0, but we'll never hit it. If we keep decreasing by a multiple of 1/2. Okay, we're always going to get really close, but it's never going to hit it. And this could actually probably be even closer to 0 right there. But it's never going to actually touch it. But we know that if a liquid cools, is it ever going to get down to 0 degrees? If it gets down to 0 degrees, that's going to be below freezing. We know 32 degrees Fahrenheit is freezing. So that doesn't make sense that this model could actually be what a liquid could cool at. So let's try to fix that. Assume a liquid starts at 200 degrees Fahrenheit and begins to cool in a room that is a steady temperature of 70 degrees. What is this going to look like if we try to draw the sketch? So we know this is our initial value. This is some time t. Our initial value is 200, right? And if it's the temperature of the room is 70 degrees, the lowest that this liquid is going to cool to must be 70 degrees. And so we know that 70 degrees is about there. We'll call it, actually I'll move it down just a little lower. Say 70 degrees is there. And if I start here, at some point I'm going to be decreasing and I'm going to level off. Not go back up there. Please do not do that. I'm going to level off at 70 degrees. And yes, I know my drawing is not perfect. But I'm going to cool off so it hits 70 degrees. And it's going to stay at a constant temperature of 70 degrees. So what is this 70? How did this graph differ from this graph? So y, equation number 1, y would be the equation not model. So we talked about this. This graph has an asymptote of y equals 0. Goes all the way to 0, except it's an asymptote, so it never touches it, but it gets really close. This, a, has an asymptote at 70. So how could we model this more realistic? Well, we have this idea that we have y equals the initial value, right? We have some rate that it's changing. We don't know what this is. We'll call it a. The time. But what happened to this graph? It was shifted up. It was transformed up. There's a transformation. If I shift a graph up, I know that I have to add a variable. We don't know what we're going to call that, but we'll call it C. Oh, and it did say B, A, B to the T, so I'll change that to B. And this would be A. But it was shifted up. That's the idea, that if I know that what the temperature of the room is, it was shifted higher. So let's look at exercise number 3. We're going to stick with the same idea of this liquid cooling. We're going to say that the idea that the initial temperature is 200 degrees. The room, again, is still 70 degrees. So which of these constants is equal to 70? Well, we talked about this before. This is the room temperature, and this was the shift up. So the C value, because it was shifted, the lowest it can get is 70 degrees. And so that's why. So that's our shift up. Now, none of these constants is equal to 200, and that's key. Our initial value, which is our A, is not 200. You're going to see why here in a minute. So please don't think that that's 200. None of these constants equal 200, but T of 0 equals 200, or F of 0, or what you want to think of that. So 200 equals A, B, 0 is our T, plus 70. Well, we've talked about this. Let's get rid of the 70 first. So we're going to subtract it. 130 equals AB to the 0. Well, what is B to the 0? Anything to the 0 power, which we talked about last lesson, is 1. So A equals 30. Oh, sorry, 130, not 30. 130. So the A value is actually 130, and let's think about why that's the case. 130 times 1 is 130, plus 70 will give us the 200 that it started at. So that's important, that our A value is not the initial value that it starts at, due to the fact that the room temperature is factoring into that. In order to find the B value, we need additional information. Well, let's think about that. What does the B value represent? The B value represents the rate at which it's cooling. Now notice that this is different for certain liquids. Different liquids cool at different rates. And so therefore, we need to figure out what B is. We need to know necessarily maybe how fast it cools, what the temperature is at a certain time, to help us figure that out. So let's look at D, which is what it gives us. After 5 minutes, it's 153 degrees. So we know that we're looking for the value of B. So we know that 153, we know that T of 5 equals 153. So we have 153 degrees equals, we found our A value, 130, B to the 5 plus 70. So the first thing that we're going to do is subtract the 70, and from that, subtract 70, and then divide by 130, right? Because that's gone and we got to get the B alone. So that's going to give us 83 divided by 130 equals B to the 5th. Notice here, the variable is not in the exponent. We're not using logs or natural logs to solve this. We are trying to solve for the base. We've talked about this before in the exponentials unit. What can we do? We're going to raise each side to the 1/5. So 83 over 130 to the 1/5 equals B, and that will give us, I know you guys could use a calculator here, but that will give us B to equal 0.91. Now we have everything that we need. Our final equation is A of T equals our A value 130, our B value 0.91 raised to the T plus 70. So what you're going to do is put that in the calculator and find out the answers. So right now, pause it please. So I hope you got these as your answers, remembering that t is in minutes, so a of 30, a of 60, a of 120. And notice here how much change really happened from 60 to 120. Not much, very little compared from 30 to 60, especially since we started at 200 degrees. So using your calculator, you can sketch this. I'm not going to use it. You are more than welcome to use it. Please do so. Our initial value is 200. We know that the lowest we can get to is 70. So our window, make sure that your window, you don't do 200 to 70. You want to see the x-axis, so do 0 to 200 for the y-axis. And our time t, you could have done all the way out to 120. I'm only going to do to 60. So your window for the x should be 0 to 60, only because not much change from 60 to 120. So it should look like this, with an asymptote, again, the horizontal asymptote at 70. And it should be very close. So again, it should even be probably looking more like this. But you can use your calculator for that. And for the final part, algebraically determine to the nearest minute, kind of one of the more important parts in graphing, when the temperature reaches 100. So we want to find when it equals 100. So we're going to have 100 equals 130.91 raised to the t plus 70 is our equation. We want to find what t is. Now notice where t is, not like the example in D where the x, we're trying to find the base. Now we're trying to find the exponent, so we will have to use logs or natural logs. And let's figure this out. So we're going to subtract the 70 over 30 equals 130.91 to the t. Divide by 130 so we can get the exponential base and function alone. And so we're going to get 30 over 130 equals 0.91 raised to the t. We do not see an e here, and so therefore we do not use natural logs. That's really important. We do not use natural logs, we only use logs, and so we're going to take the logarithm of both sides. And remember the properties of logarithms, where you have the power rule, so this t can come out in front. And so we're going to get log of 30 over 130 equals t log of 0.91. And the final step would be to divide that over, so t equals log of 30 over 130 divided by log of 0.91. And when you do that in your calculator, and yes, do it to make sure you get the correct answer, you should get 15.5 minutes. So what does that mean? If we wanted to wait to drink it or to use the liquid when it reached 100 degrees Fahrenheit, it would take 15.5 minutes to get there. Please make sure to do this in the calculator to make sure you do know how to use it. So with that ends today's lesson. To recap, we have Newton's law of cooling, where we have this idea of A times B to the T plus C, where C is the room temperature, or the lowest it can cool to. B is the rate at which it is cooling. A is not the initial temperature, though. That's a key one to remember. And we have compound interest, where it's very important to remember that compound interest is P times 1 plus the rate over how many times it's compounded raised to the t times n. Know that it's sometimes written as n times t, it's the same thing. You need to multiply those and make sure that you're multiplying them both in the exponent. It's important to you, why it's important to use the calculator. With that, it's done with day 5. Enjoy your day.